Hey guys, so today I'm going to do a video for you about the mole ratio. The mole ratio is the first major concept in a branch of chemistry called stoichiometry. Sometimes stoichiometry is just simply called stoic, and it is the study of the relationships between chemical quantities in a reaction. So all of that stuff that we did with dimensional analysis is super important, and it plays a really key role in stoichiometry. Everything we've been doing so far, it's all leading up to stoichiometry. So that's why it's so important that we really understand how to convert from grams to moles using the molar mass, or vice versa, from moles to grams. When we're talking about the mole ratio, what we really want to focus in on in a chemical reaction is the coefficients. If you remember, the coefficients, they represent the number of molecules in a reaction. So if I have the following reaction here, C4H8 plus, and this is going to be an already balanced reaction, C4H8 plus 6O2 yields 4CO2 plus 4H2O. You've seen this reaction before. Do you remember what type of reaction it is? It's a combustion reaction. So remember, the coefficients represent how many, or the number of molecules. What this reaction is telling us is that for every one molecule of C4H8, it will react with 6 molecules of O2, and it will form 4 molecules of CO2 and 4 molecules of H2O. What is another number or idea that represents how many something is? The mole. The mole represents that. So I can rewrite this equation identifying the coefficients as how many moles there are. So I can say that 1 mole of C4H8 will react with 6 moles of O2 to form 4 moles of CO2 and 4 moles of H2O. So this is the first step in understanding the mole ratio, which we're going to get to in just a moment. Now you know that the coefficients can represent how many moles there are in a chemical reaction. So I'm going to go ahead and erase this and this. But we're still going to focus on this reaction right here, okay? So the mole ratio is basically comparing two quantities of a chemical. Since all of these coefficients represent moles, I can take any of these quantities, put them together as a ratio, and I have a mole ratio. So if I were to be looking, let's look at these two compounds right here. The first ratio, 1 mole, and remember, when there's no coefficient there, there's always that imaginary 1 in front of that compound. So 1 mole of C4H8 matches up with 6 moles of O2. And that little colon there represents a ratio. What can we do with ratios? Well, when we have ratios, we can now make a conversion factor. So we can say that in this reaction, and only in this reaction, we can make a statement that 1 mole of C4H8 equals 6 moles of O2. So what do I mean by equals? I don't mean that they're the same compound. I'm talking about the quantities. For every 1 mole of C4H8, I will have 6 moles of O2. Whenever you set two things equal to each other, you can now make a conversion factor and you can create two different fractions. So I can either say that 1 mole of C4H8 goes over 6 moles of O2, or I can say that 6 moles of O2 goes over 1 mole of C4H8. So those are the two different mole ratios or conversion factors that you can use in a problem because they both mean the same thing. If you remember, just back from regular conversion factors, when you set something equal to each other, you're making a statement that these two are of equal quantities. So when you divide them by each other, they essentially equal 1. And it doesn't matter which goes on top or which goes on the bottom. Because if we're saying that they're the same, they're equal to each other, if you divide the same thing by itself, it always equals 1. That's why each of these conversion factors could work depending on what your problem is. So let's do a problem now. The problem is going to be how many moles of O2 will react with 5.5 moles of C4H8. All right, the given is that. That's the number that's given. So we know we're going to start off with this. 5 moles of C4H8. So when we do the work for these type of stoichiometry problems, we want to remember to always put the compound after the quantity. Because we're going to, in our dimensional analysis, we're going to have multiple types of moles. So we want to know which compound we're talking about. Always write the compound after the quantity. So I'm starting off with 5.5 moles of C4H8. And I want to find moles of O2. So that's what I want. I want moles of O2. Since we're talking about this reaction here, I know that I can use one of these two mole ratios to figure out my answer. So if you remember, when you're trying to figure out conversion factors, what you want goes on top. I want moles of O2. So which of these conversion factors has moles of O2 at the top? This one does. That's why I want to use this conversion factor. Another key of how do you know which conversion factor to use? What you have goes on the bottom. I have moles of C4H8. Moles of C4H8 is at the bottom. That means when I multiply the conversion factor, the bottom will cancel out. And just a reminder, you don't have to write the E when you're doing all of your math work for it. Okay, so 5.5 moles of C4H8 multiplied by the mole ratio of 6 moles of O2 per 1 mole of C4H8. So this was a one-step problem here. I just have to multiply it by one conversion factor. My moles cancel right there, right? Because it's moles of C4H8. Moles of C4H8 cancel. If I do a little bit of math, 5.5 times 6, you should get 33 moles of O2.